everyone. So this is going to be one of the last things that we talk about, which is essentially the wave equation. Now, this kind of goes back to what we've been talking about so far about this simple harmonic motion and periodic motion, all that stuff. What we're going to end up doing is we're going to try to come up with equations and graphs that represent how the object moves over time. And that's actually one of the nice things about simple harmonic motion is that they can very easily be represented by very specific motion graphs. Now, we've been calling the simple harmonic motion periodic. We've actually been using that term a lot. Now, one way that we can figure out a perfect equation to represent something like a pendulum as it oscillates back and forth, or a mass on a spring, is by trying to think about what equations that we've been dealing with that are also periodic, that repeat over time. If you think back to math, there's only one equation that makes sense, a trig function. Something like sine or cosine is an equation that repeats itself over and over and over again. And it turns out that displacement, velocity, and acceleration for pretty much any object undergoing simple harmonic motion can be represented with some sort of sine or cosine curve. Now, what we're going to do is we're actually going to try to come up with the equation for this setup. So we're going to make the assumption that we have a block attached to a spring, we elongate it to the positive amplitude, and then we let go. And we want to know, well, what would the graph look like? So if I'm starting at the amplitude, my position graph should start at some maximum value. Now, as it goes, it's going to start decreasing as it goes to the equilibrium point. So it's going to end up going to 0. Then, as it passes the equilibrium point, it's going to go to the other amplitude on the other side. So it's going to go down to here. Once it reaches that that negative amplitude, it's going to bounce back to the equilibrium point before returning back to where it starts. And then it's going to repeat this cycle over and over and over again. Well, if I connect these dots using either sine or cosine, we can quickly see that the best curve that we end up getting is a cosine curve. So for this scenario, oscillating spring starting at the positive amplitude is going to have a position graph that looks like a cosine curve. Now, we can actually get something else about this. We know that sine and cosine by themselves max at 1. That's actually one of their key features, that the max value of cosine is 1, the minimum value is 0. Same thing for sine. So if my position graph is going to have to start and is going to have to peak at some amplitude value, that means I'm going to have to multiply the cosine by this max value amplitude. So right off the bat, I can already see that my position graph should have this sort of structure: a cosine blah blah times t. The a, so that we max out at the amplitude values like we're supposed to. Cosine, because we're starting at an amplitude, going to the equilibrium and back and forward. There's going to be some stuff in here, and then we're going to have to multiply it by time, because as time progresses, this amplitude should change. So like the cosine value should be changing. Now the key feature is, what is the blah 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 part? Now you can actually try to figure out this through some sort of derivation. One way to think about it is that first off, what's a good way of putting it? For the period, when the time reaches the period, blah blah, my position should also equal the amplitude, because as we can see here, if I start at negative a, I get back to negative a. So that means that I need this cosine blah times t to equal 1. This only really happens at one specific point, when the angle, when this part equals 2 pi. So somehow I have to get 2 pi to be equal to this blah blah times t. So one way I could do this is by adding in a little frequency. The reason being is because frequency times period equals 1. So if I look back at this, 2 pi frequency times period does equal 1 because 2 pi cosine 2 pi equals 1. So we already figured out what the equation looks like. Now this equation actually is on the reference table. If you weren't too sure why the inside is 2 pi ft, don't worry too much about it. That comes from that's actually more of a math thing. It kind of comes from multivariable calculus and dimensional calculus. So if you don't understand it, don't worry about it. But we should end up with this type of equation. Now, for the most part, this is going to be true for any simple harmonic motion that starts at the positive amplitude. Now, it's important to note that all the equations and all the graphs that are going to come from this are based off of this scenario. It's important to note that if I change this, maybe instead of having it start at the positive amplitude, I have it start at the negative amplitude. Some of these things are going to change. The overall structure doesn't change, but the specifics will. So maybe instead of it being a cosine curve, it could be a sine curve. Maybe instead of it being a positive cosine, it could be negative cosine. And that's going to end up affecting all the other graphs. So what I'm trying to get at is don't focus on memorizing these specific equations and memorizing what the equation for velocity and acceleration is, but more of how we get to it. Try to remember the concepts behind it. Now, we can do something very similar about the velocity. Now, if I actually go back to the previous one, when the position is at its at the amplitude, we know that the velocity is equal to 0. So my velocity should start here. And I know every single time it reaches its amplitude, whether it's positive or negative, the velocity should always be 0. So I can actually plot 0 for all these points. Now the reason I'm showing this is because this is kind of the method that you want to go about when you're being given a graph and you're being asked to draw it yourself. You want to be able to identify, where are the values 0 so that you can put it in the right spots. Remember, amplitudes and equilibrium points. You should know what values are maximum when and what values are 0 when at both those locations. Now for here, this can get a little tricky. So we're starting at the positive amplitude. So we're starting, if I had to draw it, if this is 0, we're starting over here. This would be positive A. When I release it, it's going to go to this direction. So it's going to go to the left, and it's going to reach a maximum. So by the time it reaches the equilibrium point, it's going to reach a negative maximum. Likewise, going from the negative amplitude to the positive amplitude, it's going to be on the left-hand side being pushed to the right. So this should peak over here. And when I connect the graph, I end up seeing that I'll end up getting a negative sine curve. So this is what my velocity graph is going to look like. Again, I get it straight from the previous graph. One way to think about it, if you're kind of having issues with figuring out which should it be negative sign or positive sign, there is a way to remember it based off of the way it shifts. Pretty much every time you go up to the next one, so going from position to velocity, velocity to acceleration, you basically shift the graph over to the left, 90 degrees. But you don't have to worry about that too much. So yeah, we're going to end up having a velocity that starts at 0, peaks at the negative, 0, peaks at the positive. Again, only because of the way that the position graph looks. We could do the same thing for acceleration. So I can actually go back to this graph, and because it might actually be easier dealing with this one. So if you recall, position and acceleration actually have a fairly direct relationship, where every time the position 0, so is the acceleration. So my acceleration zeros will be right here. Now, there was one thing to remember about position and acceleration is that they're, for the most part, in opposite directions. When we are moved to the right, just like with the velocity, the spring is pulling us to the left, trying to pull us back to equilibrium. So we're going to feel an acceleration in the other direction. When it goes to the left-hand side, it's going to feel an acceleration to the right. So it's going to start at the negative amplitude and do something like this, reaching maximums every time the position reaches a maximum, but in the other direction. So our graph is going to look like this. Now they drew it a little bit bigger, but it doesn't really matter. One thing to pay attention about all three of these graphs is, if you'll notice, they all have the same period. And that's actually extremely important, that each of these graphs will start and end their cycle at the same time. The reason why this is important is because you're guaranteed to have to draw one of these graphs on the AP and even on the test. The reason why that's important is because one of the points that you'll be awarded is to make sure that your graph has the same period as the other graph. So if they graph one cycle in 2 seconds, you need to make sure that whatever type of graph you make, whether it's a sine curve or a cosine curve, that you make sure that it has the same 2-second period as the other one. If you try to put 2 waves in that 2 seconds, you'll lose points. It's also important that you note, you make sure that you evenly space out the sine curve or the trig function. So like, for example, let's say you were going to make a sine curve and you did something like this, where it goes up and then, does something like that. We'll pretend like I actually crossed that point. Now this is what looks like a sine curve, and it does have a period of same as this one. But notice how this first crest, the top part, is much bigger than the other side. Because of this unevenness, you'll lose a point. So I usually tell people that when you're going to graph this stuff, it's actually extremely helpful to plot out exactly where your zeros are. I'm going to want to put zeros here, where your maximum values are. And then from there, connect the dots, and you'll end up having a perfect sine curve or cosine curve every single time. Now, how can we be sure that these are the correct graphs? Like I said, I've been using conceptual understanding for that. Now, for the most part, that's really all you need to do. However, I want to make a very quick comment for those people that take calculus. While there are a few cases here and there in the class where you could use calculus, it never really is that useful, mostly because of the fact that anytime you would want to use calculus to find the area or the slope of something, you're usually given a graph, which means that you would have to figure out what the equation is for that graph and then take the derivative and slope, which could be a lot of effort. This one, though, on the other hand, this one's a little bit easier to use calculus for. So I'm going to show that right now. All right, so what we can do is we can actually take the derivative. Like I said, for anyone who has taken calculus or has dabbled in it, you know that there's these things called derivatives and integrals. And if we have a position equation, taking the derivative of it gets us velocity. So taking the derivative of a cosine curve, you multiply the coefficient by basically the derivative of what's inside, which is 2 pi times frequency. And then the cosine turns into negative sine. So in the end, you end up with the velocity being negative a times 2 pi frequency sine of 2 pi frequency t. We don't really like this inner term. So what we're going to do is we're going to actually replace this with the term Vmax, because just like with the position, the entire coefficient in front of these trig functions are the max values. So the equation ends up being negative Vmax sine of 2 pi ft. So again, we end up seeing that from here we get a negative sine curve with the exact same frequency and same period as we had before. Likewise, I could do the same thing for acceleration. So I could take my velocity equation, take the derivative of it. Same thing happens. This time sine just turns into cosine. And once again, the 2 pi times f gets pulled out and multiplied by the coefficient. And again, just like last time, we take this entire term and replace it with a max. So we end up with negative a max cosine 2 pi ft. And again, exactly what we had last time. We had a negative cosine curve. So now, like I said, you don't have to do derivatives. There's all these other ways that you could figure it out. Like I said, though, usually you'd have to go with conceptual. I just want to show this because a lot of people that are taking AP Physics have taken at least calculus or maybe even pre-calc. They're kind of in that mindset of taking derivatives. So this is actually one of those few cases where you actually can take a derivative of an equation, because the equation is going to be something that you're going to end up coming up with, unlike some of the other problems that we've done. All right. Now, some key things that you want to remember is that all these graphs, displacement, velocity, and acceleration, all have the same period and frequency. It's important to remember that these three graphs do not have the same maximums. The maximums are kind of related, and there's ways to figure out the maximums. I didn't show it before, but one thing you could do is actually set, for example, if you have the max position, the amplitude, you can actually find Vmax by doing max kinetic energy equal to max potential energy. Likewise, I can find position. Using my max amplitude, I can actually find my max acceleration by doing forces. At the equilibrium point, the spring force is going, or actually throughout the process, I should say, the spring force is going to be equal to the net force equals ma. So we have kx equals ma. We can use that to find the acceleration. So we can use conservation of energy. We can use forces to figure out the relationship between amplitude, Vmax, and Amax, if you didn't want to go the calculus route. And also, like I said, it's important to remember that displacement and acceleration should always have the same trig function. Velocity is going to be the other one. So if our displacement's cosine, then velocity sine. If displacement sine, velocity is cosine. It's also important to remember that acceleration and displacement are opposite functions. So if displacement is positive cosine, acceleration is negative cosine. If displacement was positive sine, acceleration is negative sine. All right. So all three graphs are going to end up looking like this. And like I said, this is just one scenario. I can alter one of these graphs and you should be able to know how all the other graphs come about. All right, so work on this question. Pause the video, work yourself, and we'll go over in a second. Now for this question, I don't actually really care the specific graph. I didn't really give you enough information to figure out what the amplitudes are or whether it should be sine or cosine. So all I really care about is that you drew two trig functions, one with the period of 6 seconds and the other with twice the frequency. So let's start with the first one, the period of 6 seconds. What I'm going to do is I'm going to draw a sine curve, and I'm going to first pinpoint all the points where it's at the equilibrium point. So since it's a sine curve, it's going to start at the equilibrium point and it's going to end at the equilibrium point. So I should have a point at the zero, both at 0 and 6 seconds. Halfway in between is going to be another equilibrium point, which is going to be right there at 3 seconds. Then my amplitudes are going to occur halfway between these 2 points. So halfway between 0 and 3 is 1.5. So I'll make that positive amplitude, not like it matters. Halfway between 3 and 6 is 4.5. So that's the other amplitude. And then I just connect the dots, and I end up getting a sine curve. So this is going to be my first period of 6 seconds. Now they want us to draw an object with twice the frequency. So what we could do is, if we forgot what that would mean, I could do the 1-1 method, so twice the frequency. So let's see. Yeah, I'll just do it this way. Twice the frequency means that the period is half of the original value. So my original period was 6 seconds, so my new period is going to be 3 seconds. So I'm going to make a sine curve the same exact way. At 0 and 3 are my beginning and ending points. Halfway in between is going to be the second equilibrium point. So that's going to be at 1.5 seconds. Then halfway between these two is going to be my first amplitude. Halfway between the other two equilibrium points is my second amplitude. And once again, I connect the dots. So this is my graph for a period of 6 seconds, and this is going to be the twice the frequency. Again, you might have drawn it a little bit differently. Maybe you drew it with a greater amplitude. Maybe you drew it as a sine, as a negative sign or a cosine curve. Doesn't matter. What mattered is basically getting the trig function drawn properly and understanding how to do twice the frequency. All right. This will be the last one that we do today. So pause video, work cell phone over in a second. All right. So which color has the greatest frequency? Well, just looking at this, we can immediately see that this is the one that we see the most frequent. So purple is going to be the one with the greatest frequency. Color that has the greatest period, one way we can think about it is the one that takes the longest to complete a cycle, or we could think about the one that we see the least. But whatever the answer is, it's going to be red, this one. All right. And that's pretty much it. So like I said, the big takeaway is you should be able to know which trig function to use based off of the scenarios, and you should be able to know how to use their max values to figure out the other parts of it. All right, if you have any questions, feel free to let me know. Otherwise, good luck and have a great day.